Hello, everyone. Today, we're diving into isomerism. Now, this is a topic that comes up a lot in the DSC chemistry paper, and I know it can feel a little tricky at first. But trust me, by the end of this explainer, you're going to have a really solid grip on it. So, let's jump right in.
So let's kick things off with a little puzzle. Look at this molecular formula, C4H10. Simple enough, right? But here's the thing. This formula can actually describe two totally different compounds. One of them boils at minus 0.5 degrees Celsius, but the other boils way colder, at minus 11.7. So if they're built from the exact same atoms, 4 carbons, 10 hydrogens, how on earth can they be so different? Well, the answer is isomerism.
Okay, this right here is the absolute core definition you need to know. Isomers are compounds that share the exact same molecular formula, but, and this is the key part, they have a different arrangement of atoms. The best way to think about it is like having a set of Lego bricks. You've got the same number and color of bricks, but you can build them into completely different shapes. That's what isomers are.
To make sense of all this, we're going to use this chart as our roadmap. You can think of it as the isomer family tree. See how it splits into two main branches. We're going to explore both of those branches and meet all the different types of isomers along the way.
Okay, first up, this big branch over here, structural isomers. Now for this whole group, the fundamental difference is all about the connectivity. The atoms are literally connected to each other in a different sequence. It's not just a different shape, it's a whole different molecular blueprint.
First up in this family, we have chain isomers, and the name pretty much tells you everything you need to know. They have different carbon chains, or carbon skeletons. Let's go back to our C4H10 example. On the left, you see butane. That's a straight, unbranched chain of 4 carbons. But on the right, we have methylpropane. The main chain is only 3 carbons long, with another carbon branching off the middle. Same exact parts, just a different backbone. Next, we've got position isomers. Now listen closely because this is a classic DSE trap. Unlike chain isomers, here the carbon skeleton is exactly the same. What's different is the position of the functional group. Take a look at these two. On the left, propan-1-ol, the OH group is on the first carbon. On the right, propan-2-ol, the OH group has moved to the second carbon. Same 3-carbon chain, but the functional group is in a different spot. And the last type in this branch is functional group isomerism. Now remember, the functional group is what gives a molecule its chemical personality. Well, these isomers have the same molecular formula, but completely different functional groups. That means they belong to totally different families of organic compounds. For example, C4H8O2 could be butynoic acid, which is a carboxylic acid, or it could be ethyl ethanoate, an ester. Same atoms, but wildly different chemical properties.
All right, time for a quick checkpoint. Take a second and think about it. Based on what we just saw, what's the one key difference you'd use to tell a chain isomer apart from a position isomer? What's changing in each case?
Okay, let's head over to the second main branch of our family tree, stereoisomers. This is where things get a little more 3D. With stereoisomers, the atom-to-atom connections are actually the same. The blueprint is identical. The difference is all about how those atoms are arranged in 3-dimensional space.
So the first type of stereoisomer we're going to look at is called cis-trans isomerism. And honestly, this whole idea boils down to one simple but super important fact. A carbon-carbon double bond is rigid. It's locked. Unlike a single bond, which can spin freely, a double bond can't rotate. And that lack of rotation is precisely why cis-trans isomers can even exist. You see, because that double bond is locked, all the atoms or groups attached to those carbons are stuck in their positions relative to each other. They're fixed in space. This slide shows it perfectly. Look at the molecule on the left. See how the two green chlorine atoms are both on the same side of that double bond? That's what we call the cis isomer. Cis means same side. Now look to the right. The chlorines are on opposite sides of the double bond. That's the trans isomer. Trans basically means across.
So, for your exam, here's your 2-point checklist. For a molecule to have cis-trans isomers, it has to meet 2 conditions. Number 1, you got to have a carbon-carbon double bond. That's a given. And number 2, this is the one people forget, each of the 2 carbons in that double bond must be attached to 2 different groups. If one of those carbons is holding 2 of the same thing, it's game over. No cis-trans isomerism.
Okay, another quick checkpoint. Think about the molecule 1,1-dichloroethene. Now, based on those 2 rules we just talked about, can you figure out why that molecule can't have cis-trans isomers? Which rule does it break?
All right, let's keep going down this stereoisomer branch and talk about a really fascinating type of isomer called enantiomers.
You'll often hear these called mirror image isomers, and you're about to see exactly why.
Honestly, the absolute best way to understand this is to just look down at your own hands. It's the perfect real-world example.
So, your left hand is a perfect mirror image of your right hand, right? But now try to lay them on top of each other so that they match up perfectly, palm to palm, thumb on thumb. You can't do it. They're what we call non-superimposable. And this property, this handedness, is called chirality.
And this is exactly what happens with some molecules. Look here. On the left is one version of a molecule, and on the right is its reflection in a mirror. They are definitely mirror images. But just like your hands, if you tried to drag one on top of the other, they would never line up perfectly. They are non-superimposable mirror images. A pair of molecules like this, we call them enantiomers.
So, how can you spot a molecule that has an enantiomer? What's the secret? You have to hunt for something called a chiral carbon. And a chiral carbon is simply a carbon atom that is bonded to 4 completely different things. If a molecule has one of these, that carbon acts as a center of asymmetry, and the whole molecule becomes chiral.
Okay, let's just quickly check our understanding here. How would you describe the relationship between a chiral molecule and its enantiomer? What are the 2 key things that define them?
Phew! Okay, we have now traveled down both of the main branches, and we've met all the key members of the isomer family. So now, let's take a step back and look at our complete map all put together.
And there it is, the whole picture. It's so important you know this chart. Isomers split into 2 big groups: structural isomers, where the atoms are connected differently, and stereoisomers, where the 3D layout is different. And then within each of those, you have the specific types we've just covered. This chart is basically your guide to solving any isomerism problem they throw at you in the DSC.
So to finish up, I want to leave you with a thought that shows why this isn't just exam theory. It's actually a matter of life and death. You see, the receptors in our body are also chiral. They're like tiny, 3-dimensional locks. So think about this. Why might one enantiomer be the perfect key that fits the lock and acts as a life-saving drug, while its mirror image twin is completely useless, or even worse, harmful? It's a really powerful reminder of just how much a molecule's 3D shape truly matters. Thanks for watching, and good luck with your studies.